At this point, he develops two technical lemmas, and then the rest of the section is basically devoted to showing you that if you look at isometries, I'll just tell you what happens. We prove through the rest of the section, we prove that isometries take geodesics to geodesics, just like you'd expect, like the image of a geodesic is a geodesic under the isometry. All right? And we also prove that the connection is, here I'll write down the formula. We prove this, that the connection bar of phi star x, I'll write it down so we can talk about it, of push forward of y is equal to the push forward of nabla x of y. So what's this say? So here's what I'm talking about is this is the connection built from the metric on the isometric space, right? And what this is saying is that the connection between the connection between the connection on the given Riemannian space and the related isometric space is just this. There's a natural relation between the connection on the original space and the corresponding isometric space, and it's just the natural one. That actually is what he uses to prove the geodesics, map to geodesics. And you can actually use that. You can actually use that principle to take the isometry. Remember the one we just had, the minus reciprocal map on the half plane. So think about that. You guys proved that you proved that a vertical line segment's a geodesic in one of your homeworks, right? So the fact that the minus 1 over z map is an isometry of the half plane means that the image of the vertical line segment through the minus reciprocal map is also going to be a geodesic. And that gives you a proof that the vertical line segment, which maps to a half circle or something like that, is also a geodesic. Basically, once you have one geodesic and you have isometries, you can feed that data that you have and create new data by just moving it around with the group. It's a way of generating new solutions from a given solution using the group. It's quite beautiful. More than this, though, you can prove curvature is transported naturally by isometry. And the curvature tensor, the Ricci scalar, all of it. Because all of those things are naturally built from the metric. And the fact that the metric is preserved means that all of the data that's built from the metric is also preserved. Now, you actually have to prove that. That's just a slogan I'm telling you. But the slogan is proved in this section. And that brings us to Gauss's awesome theorem, or his theorem egregium, which says that if you have a regular parametrization of a surface and you have a metric tensor, well, tell you what, let me not say it. Let me show you a picture of it. Haha. Excellent. So this is well, at least if the projector didn't work right now, it's good, because I would have gotten so very angry right now if it didn't work. I'll tell you that. So I'm very happy that it worked. Saved my anger for parking in New York City. It's good. Come on, you can do it. You can do it. Here we go. So Gauss's theorem egregium, which means remarkable theorem or like totally awesome theorem, it says basically that the Gaussian curvature of a surface does not change if one bends the surface without stretching it. Now, I guess it doesn't look that way in our current way of thinking, but it basically says that the Gaussian curvature, if you have it actually says this, if you have a local isometry, then the Gaussian curvature doesn't change under one of those local isometries, So this picture we're looking at here is a picture of the catenoid and the helicoid and how you can smoothly deform one to the other without changing the geometry. They both have the same Gaussian curvature. That's why you can map one to the other They're actually both examples of what are called minimal surfaces, which have ties in with soap bubbles and so forth. But again, the Gaussian curvature of a surface is an invariant under the local isometry. And so, by the way, that means that there's no way you can smoothly, without tearing. So like losing a concept of local distance, right? Like changing the distance between points locally amounts to tearing paper. So Gauss's theorem implies that you can't make a flat map of the Earth, because we can calculate the Gaussian curvature for a sphere, and it's non-zero. It's actually constant. It's constant everywhere. I think it's 1 over the radius of the sphere squared, up to a convention, I forget. And so, on the other hand, the Gaussian curvature of a flat sheet of paper is 0. So there's no way you can isometrically map the sphere to, the flat thing without. Anyway, so that's one of the interesting applications this website here points out, which is, I don't know what this website is. Unfortunately, the HTML is not very conductive to me explaining where this is from. I found it Googling. It looks like Wikipedia. Distributed Wikipedia. Distributed Wikipedia? I don't know what that is. But apparently it's what we're looking at. So I thought I should also mention a word or two about general relativity here while I'm picking up some loose ends and sharing some general fun facts with you here at the end of the day. This right here, what you're looking at is Einstein's field equations. I thought I should at least mention them to you since we have almost everything we need to understand them. Kind of understand them. This is the Ricci tensor. This is the Ricci scalar. This is the stress-energy tensor, which includes like energy and momentum in space-time. All right, this would include everything from electric and magnetic fields to, the momentum of a baseball, whatever. Everything you've ever learned in physics, every matter, energy thing you've learned in physics gets put into this. Okay? And this is g, as in the gravitational constant. That's the speed of light to the 4th power, apparently. Now, you might wonder what this is. That's the cosmological constant, which we threw away about, I don't know, how many years ago? Early on, Einstein realized this was a possibility, but he said, threw it away. But lately, we've come to believe that it has to be there for various large-scale cosmological observations. It's needed. And, but that term is just proportional to the metric g. And so these are Einstein field equations. And those are what you got to solve if you want to try to unravel general relativity. So there. Don't say I never taught you any general relativity. Math. So one of the interesting things we could teach you in complex analysis, but we probably won't because I don't think I did either. But this is the sort of penultimate goal of better complex variables books, is to explain what's called the uniformization theorem. And the uniformization theorem, which I can't say today, says that every Riemann surface is the quotient of a free, proper, holomorphic action of the discrete group on the universal covering. And this universal covering is holomorphically isomorphic to one of the following: the Riemann sphere, the complex plane, or the unit disk in the complex plane. So the Riemann sphere, we've played with some in here, actually. That was that stereographic projection problem you guys had. That's that thing. The complex plane, well, that's the complex plane. And then the unit disk in the complex plane. These are, in some sense, general categorizations of what you find for compact Riemann surfaces up to this fine print. What's a Riemann surface? It's the kind of the graph of a complex function, if you were to try to think about it. That's a little bit of a lie, but when you study complex analysis, you'll learn what a Riemann surface is. It's a natural thing to look at, but So that's the uniformization theorem. Now, of course, that's fairly old. We're talking 19th century there. That was learned. So naturally, people wanted to go up a dimension and say, well, what about 3 dimensions? If we narrow our focus and look at sort of like compact 3-dimensional things, is there, what's out there? All right, is there, I mean, people knew about examples of 3-dimensional manifolds, and you start to wonder, are there sort of like standard shapes that they have to have? Could we look at different 3-dimensional manifolds and decide whether or not they have the same geometry? I mean, what are the different kinds of geometry possible for 3 manifolds? And so the impetus for this study in part stems from this thing called the Ricci flow. And this was basically introduced by Hamilton in 1981, and it was ultimately used by Gregory Perelman to solve what's called the Poincare conjecture, as I'll be trying to explain over the next few minutes. Let me just skip ahead here, try to explain to you what the idea of the Ricci flow is. I mean, here's the equations of it. The Ricci flow is a geometric evolution equation. It's something like partial t gij is equal to minus 2. This is the Ricci tensor. This is the metric. And you're not looking at one metric. So the idea is something like this. You look at a manifold and look at a family of metrics on the manifold, and then imagine them sort of evolving in time, although it's not really time. It's some parameter, which you're toggling through different metrics, something like this. And the Ricci flow says that they should satisfy that equation, or this equation, which involves some of the geometric data we've looked at. Here's some sort of slogans for it. Informally, the Ricci flow tends towards negatively curved regions of the manifold, and it tends to contract positively. So it expands negative curvature regions, and it contracts positively curved regions. There's something really pretty, it says a little bit further down here. So one special kind of manifold is, well, of course, Euclidean space. This is kind of a boring case. It's Ricci flat. The Ricci flow leaves the metric unchanged. All right, so any metric is unchanged. Any metric unchanged by Ricci flow is Ricci flat. All right. So there's something I'm glossing over here, but another example would be a sphere, or more generally, something with an Einstein metric. So an Einstein metric is something where the Ricci tensor is just proportional to the metric tensor. This makes it an Einstein metric. And he says, in that case, the Ricci flow collapses the manifold to a point in finite time. For example, if you take the metric of a n-dimensional sphere of radius 1 after time t, the radius is like that. So it collapses after that much time. So the idea here is that Ricci flow sometimes cannot be continued for all time. Instead, it collapses manifolds to a point, to a singularity. On the other hand, if the manifold is an Einstein manifold with negative curvature, then the Ricci flow will expand it. All right. There are also these things called Ricci solitons, which is something that Tom Wares at Longwood has done some stuff on. Something related to that anyway. That's the kind of thing he's into. And him and many other people, I suppose. But anyway, so getting ahead in the story a little bit here. The Hamilton's idea in 1981 was actually trying to tag on to this idea by William Thurston, who's a Fields medalist. He had something called the Geometrization conjecture. And so what it is a topological classification of 3-dimensional smooth manifolds. So I'm trying to find the thing I want to read to you here. Here it is. Hamilton succeeded in proving that any smooth closed 3-manifold which admits a metric of positive Ricci curvature also admits a unique Thurston geometry, namely a spherical metric, which does indeed act like an attracting fixed point of the Ricci flow, renormalized to preserve volume. All right, so that doesn't prove. So his idea was that this Ricci flow could be used perhaps to prove Thurston's conjecture about there being these 8 topologically distinct manifolds out there. And the idea was something like, again, you take one of these manifolds, we're talking topologically, so you could have different metrics on the same topological manifold, and somehow if you let that flow with respect to the Ricci flow, it will, after some time, flow into one of those 8 specific Thurston models. So that was the hope. Kind of like you have water going down a hill and there's like 8 drains. It has to eventually go into one of those 8. So the program was to prove that that actually happens after Thurston made this conjecture. People were trying to prove this for a long time. So anyway, I'm not doing it justice, but here's some technical details. Let's see here. So to be a little bit more specific here, Thurston's geometric conjecture states that certain 3-dimensional topological spaces each have a unique geometric structure that can be associated with them. It's the analog of the uniformization theorem for 2-dimensional surfaces. All right. So in 3 dimension, it's not always possible to assign a single geometry to a topological space. Instead, the geometrization conjecture states that every closed 3 manifold can be decomposed in a canonical way into pieces which either have one of the 8 types of geometric structures. So what I was just saying isn't quite accurate. The point is, you can find different pieces which are one of these sort of 8 shapes in some sort of systematic way. So let's see here. This also implies other conjectures such as the Poincare conjecture and Thurston's elliptization conjecture. Let's get on to the point here. So Gregory Perelman sketched a proof of the full geometrization conjecture in 2003 using Ricci flow with surgery. Surgery, what that means is when you have that collapsing to a point, then you do some sort of topological sewing around it to keep going. Like you don't get stuck into the fixed point. You somehow like go around the point with some sort of surgery. Is roughly the idea. The 8 model geometries, here they are. You have spherical, Euclidean, hyperbolic, H3, S2 cross R, H2 cross R, the geometry of the universal cover of SL2R, nil geometry, and then this guy, solved geometry. These are your standard examples, your standard model geometries of 3-dimensional compact manifolds. I've tried to calculate some things in some of those. It's fun. And so here is a statement, a more careful statement of Thurston's conjecture, which I've been trying to explain. Every oriented prime, what does that mean? Prime closed 3 manifold can be cut along tori so that the interior of each resulting manifold has a geometric structure with finite volume. And there are 8 possible geometric structures in 3 dimensions described in the next section. All right. All right. So here's some more of the fine print for the 8 different models. Euclidean, we've been studying that a fair amount here. Spherical. And each of these is described in terms of a Lie group acting. They're all described as homogeneous spaces, which is a particular way of constructing manifolds. Details that don't really concern us at the moment, but so history is kind of more interesting to us at the moment, right? So the Fields Medal was awarded to Thurston in 1982 for partially for his proof of the geometrization conjecture for a particular kind of manifolds, right? And then the case of 3 manifolds that should be spherical has been slower, but after Hamilton invented the Ricci flow in '82, he made some progress on it, but then later the full proof fell to Perelman, who showed that the Ricci flow can be indeed continued past the singularities and then it has the behavior described above. Anyway, Perlman's a very, very interesting character in mathematics. I mean, you should read about him. The way he behaved, the way he responded to being honored is somewhat unusual. And I don't know, he seems like a kind of fun guy. Let's see here. So, you've heard me try to explain it with words, but some things are better left to music. Ah, no! I thought I put stupid, come on. Why isn't it making noise? Oh.
When your Ricci flow stops at one geometry, one geometry, one geometry, if every loop contracts, there's no topology, no topology, no topology, so Poincare is correct. In dimension 3, in dimension 3, in dimension 3, he's just an unemployed John who's living with his mom, but his name is Perelman, so he's got it going on. Poincare is a nice dude, with some nice dreams, invent topology. For all his math schemes, 3-body problem can't solve the closed form. Find the features of the shape which still believe in before.
Sorry. Un momento, por favor. I need to, it's not big enough, right? I've got the words over here because he's hard to understand. So let me make the words bigger.
Never will contract. You can try it if you doubt me, and you'll see that I'm correct. Has to be a sphere. Every loop is not like that billion out of Fabergé. A is just called 2 dimensions all right, but we're living in 3. Circles all about this. Does it have to be a 3 sphere? He tried to see if it was true, using all that math. Tried to prove that. Even math seem to manage. You should think about it. Take a second. Matter of fact, you can take a century. Think before you mess with little Henry. When your Ricci flow stops at one geometry, one geometry, one geometry. If every loop contracts, there's no topology, no topology, no topology. So Poincare is correct. In dimension 3, in dimension 3, in dimension 3. He's just an unemployed John who's living with his mom, but his name is Perelman, so he's got it going on. I'm a math geek. You don't do that. Pass me a theorem. Yeah, I know that it was perfect eyes to smell. And if I were OG, really the tricky. Yeah, I mean OG. So the convention we're ready to sign it. Guess the one where Poincare makes right. 2, the 5, the 3. E-O-I-N, C-A-R-E. Thurston is person to not say what Thurston he specialized in looking at all the 3 folds. Listen said every 3 fold has a best geometry to maximize a group of global symmetry. Don't know how to prove this, but I showed it got a drizzle. Cause every math geek wants to earn and play crystal. Where the fields metal, the chisel, the bezel, and not Poincare. That lady's here we gives it when your Ricci flow stops at one geometry, one geometry, one geometry. If every loop contracts, there's no topology, no topology, no topology. So Poincare is correct. In dimension 3, in dimension 3, in dimension 3. He's just an unemployed John who's living with his mom, but his name is Perelman, so he's got it going on. Ricci flows bad. One of them diffuse to your geometry. Cause it to diffuse. If it plays out smooth through the end of time, it's one of Thurston's 10. Everything is fine. That was Hamilton's plan. Waiting for the man with the proof. Dog, that was Perelman. Oh, you want to form some singularity? Ricci flows surgery. Now, try and stop me. Excessive line. It's like some black hole. Spawns another. You're playing whack-a-mole. We need an entropy. Yeah, we should found it. Let's start remind you why we have to bound it. Hound it to 0 pound till it's round up and down. Students music. QED sounds up. Subscribe, fool. Know what the nerds know.
Subscribe, fool.
Because when your Ricci flow stops at one geometry, one geometry, one geometry. If every loop contracts, there's no topology, no topology, no topology. So Poincare is correct. In dimension 3, in dimension 3, in dimension 3, he's just an unemployed clown who's living with his mom, but his name is Carol Mom, so he's got it going on. Shut up! Everybody now. Shut up!
Have a good break.